An important vector space related to a matrix A is the space of all solutions to the system of equations AX equals 0. That's called the null space of the matrix A. Nullity is the dimension of that space. So if we have this matrix A, which is an m by n matrix with real entries, we define the null space of A to be all of the vectors in Rn such that AX, A times that vector equals 0. And we define the nullity of A to be the dimension of the null space of A. The nullity of A is closely related to the rank of A. In particular, for A in m by n matrix, the rank of A plus the nullity of A equals n, which is the number of columns. To see this, let's let E be a row echelon form matrix equivalent to A. Then we know that rank of A equals the number of columns of E containing leading ones. And the null space of A is the solutions to AX equals 0, or equivalently EX equals 0, because they have the same solutions. Now this is the number of free variables in EX equals 0. In other words, the number of columns of E that do not have a leading one. So we have the number of columns containing leading ones and the number of columns not containing leading ones. Well, that's all the columns. So that means that I said null space is the number of solutions. Null space is the set of solutions. This, I should have said the dimension of this is because the null space is a whole vector space, and then the number of free variables is just the dimension of that vector space. So that means that n equals the total number of columns equals columns with a leading one, which is rank, plus number of columns without a leading 1, which is nullity. So let's do an example and look at that and see that the numbers add up. So for example, let's find bases for the column space and the null space of A. Now the dimension of the column space is equal to the dimension of the row space, which is rank. And then the dimension of null space is going to be the nullity of A. And let's let A be the matrix 1, 1, 0, 1, 2, 2, negative 1, 3, negative 1, 1, and 0, 3, 3, 0, negative 1. So we'll use row operations to get to row echelon form. And then the columns containing 1s are going to tell us which columns of A we use to form a vector, to form a basis of the column space. So let's do row 2 becomes row 2 minus 2 times row 1. Then we've got 1, 1, 0, 1, 2. 2 minus 2 is 0. Negative 1 minus 2 is negative 3. 3 minus 0 is 3. Negative 1 minus 2 is negative 3. 1 minus 4 is again negative 3. And then we've got 0, 3, 3, 0, 1. Now I could divide by negative 3 here, but I'm tempted to just add these two together to make a 0 there, because I don't need to get a 1 here and then subtract 3 copies of it. So let's say 3 becomes 3 plus 2. And we've got 1, 1, 0, 1, 2, 0, negative 3, 3, negative 3, negative 3, and 0. 3 plus negative 3 is 0. 3 plus 3 is 6. 0 plus negative 3 is negative 3. 1 minus 3 is negative 2. And now let me divide the second row by negative 3 and the third row by 6. So 2 becomes negative 1/3 of 2, and 3 becomes 1/6 of 3. So we have 1, 1, 0, 1, 2, 0, 1, negative 1, 1, 1, and 0, 0, 6 divided by 6 is 1, negative 3, 6 is negative 1/2, negative 2, 6 is negative 1/3. So here are the columns with the leading 1s. So a basis for the column space of A is the first 3 columns of A. So 1, 2, 0, 1, negative 1, 3, 0, 3, 3. And the dimension of that is the rank. So rank of A apparently equals 3. Now to describe the null space, we have to set this equal to 0. The null space of A is equal to the null space of E. All the solutions to this matrix X equals 0. So we'll add a column of zeros. So we have 1, 1, 0, 1, 2, 0, 1, negative 1, well, 0, 0, 1, negative 1, 1, 1, 0, and 0, 0, 1, negative 1/2, negative 1/3, 0. So according to well, we've got two free variables, the fourth variable and the fifth variable. So let's let let's let x5 be t. And x4 be s. Then we can solve for x3, x2, and x1. x3 minus 1/2 s minus 1/3 t equals 0. So that means that x3 equals 1/2 s plus 1/3 t. So the next equation up tells us that x2 minus x3 plus s plus t equals 0. So that means that x2 equals x3 minus s minus t equals x3 half s plus 1/3 t minus s minus t. Which is 1/2 s minus s is negative 1/2 s, and 1/3 t minus t is negative 2/3 t. And then the first equation tells us that x1 plus x2 plus s plus 2t equals 0. So that means that x1 equals minus x2, 1/2 s plus 2/3 t, minus s minus 2t. So 1/2 s minus s is negative 1/2 s again. 2/3 t minus 6/3 t is negative 4/3 t. So x1, x2, x3, x4, x5 equal x1 is negative 1/2 s minus 4/3 t. x2 is negative 1/2 s minus 2/3 t. x3 is 1/2 s plus 1/3 t. x4 is s, and then x5 is t. Now if we factor out the s and the t from these vectors, we've got s times negative 1/2, negative 1/2, 1/2, 1, 0, and t times negative 4/3, negative 2/3, 1/3, 0, 1. Now these vectors multiplying the S and T are precisely a basis for the null space. So negative 1/2, negative 1/2, 1/2, 1, 0, and negative 1/3, negative 4/3, negative 2/3, 1/3, 0, 1. Now notice the column space has dimension 3, the null space has dimension 2. 3 plus 2 is 5, which is the number of columns of the matrix A. But the column space is a subspace of R3, which is how tall the columns are, and the null space is a subspace of R5, which is how long the rows are. So even though 3 plus 2 add up to 5, these are not subspaces of the same space. They're subspaces of different spaces. And another point of view that I want to point out for getting a basis of the null space is that we could set the free variables equal to 1 at a time. So set one of them equal to 1, everything else equal to 0, and then the next one equal to 1 and everything else equal to 0. So if we set s equal to 1 first and t equal to 0, when t is equal to 0, this whole thing is going to disappear. And when s is equal to 1, we're going to get this column vector next to s. So that's another way to think about getting the first column vector. And then if we set t equal to 1 and s equal to 0, when s is 0, this whole thing disappears. When t is 1, we're just copying the vector next to t. And that's another way to get the second basis vector here. So nullity of A equals the dimension of the null space of A, which is 2. And the rank of A is the dimension of the column space, which is 3 here. And 3 plus 2 equals 5, which is the number of columns of A. The end.